Hello, everyone. Thank you very much, Henry, for the introduction. I'm going to talk a little bit about the localization of dye with neutrons. And looking at the title, you may ask yourself, why do we need neutrons? Because actually, if you look at the samples, it's quite easy to see which samples contain dye and which don't. And actually, you can even visually distinguish the two ones in the middle, they contain some kind of violet dye. The one to the left or to the right from your side contains some kind of orange dye. It's easy, right? Now, what if I told you that all of these samples contain the same dye molecule called blue? The fascinating thing about dye molecules is that they actually respond to their chemical environment in terms of a change in the absorption spectrum quite often. And this is, for example, exploited if you want to check the pH of your solution using a normal pH indicator paper. Now, the dye I'm investigating at the moment is also responsive to pH, being deprotonated at its phenolic OH group in an alkaline environment, but being protonated in an acidic environment, which leads to a complete change in its absorption spectrum. But there are other factors influencing dye absorption apart from the pH. For example, aggregation due to dipole-dipole interaction with other dye molecules, or change in the polarity of the environment of the dye. For example, by addition of other components such as surfactant molecules. And the interaction between dye and surfactant is actually very relevant in industry, because very many dyeing baths or dyeing liquors for industrial application contain surfactant molecules in addition to these dye molecules. Now, surfactant molecules like to assemble into supramolecular structure. And by adding these dyes into a dyeing solution, these surfactants may interact with the dye molecules, which furthermore influences the interaction of the dye with the actual substrate that we want to dye. And my job is to find out which aggregates are formed between the dye and the surfactant. And the way to go here is to use small angle neutron scattering to investigate the morphology of the aggregates, meaning their shape and size, but also to locate the dye within the aggregates by using a technique called contrast variation. And contrast variation is based on isotopic substitution. We've heard of this today. And actually doing this, we managed to investigate a system between the anionic dye blue, which I've shown before, and the cationic surfactant DTAB. Now, first of all, you have to know that not all solutions of this dye and the surfactant are stable. And actually, the samples phase separate above a certain threshold concentration of, or the threshold ratio between the dye and the surfactant. It's all an aqueous solution, by the way. Now, for the small angle neutron scattering, we focused on the soluble part, going from the phase transition threshold into the more surfactant-rich side, where we found that leaving the phase transition threshold into the surfactant-rich side, we found a decrease in anisotropy of the aggregates that were formed. Also, by performing contrast variation experiments, we were able to localize the dye molecules on the outside of the dye surfactant micelle. Now, this is still quite fundamental research, but it may help us to understand the interactions that are involved in dyeing formulations and may help us to design more efficient system in the future. But for this, it's also important to look at other factors, for example, dye self-aggregation, which I've studied before, or the impact of pH on solutions containing dye and surfactant, which I'm currently working on. And with this, I would like to thank you for your attention.